Hello everyone, welcome to lecture 2 of sound. So in this lecture we'll start with harmonics. So we'll try to differentiate the harmonic series of open and closed pipes, calculate the harmonics of a vibrating string and of closed and open pipes, and relate harmonics and timbre, and relate the frequency difference between two waves to the number of beats heard per second. So let's start with standing waves. So we already discussed standing waves in the last topic when we discussed vibration and waves. So standing waves, when you have a vibrating string, so the vibrations of the string of a musical instrument generally contains many standing waves, and each of these will have their own wavelength and frequency. So the greatest possible wavelength on a string is given as lambda equals 2L, and the fundamental frequency which corresponds to the wavelength is the lowest frequency of the vibration. So we know that frequency is velocity by wavelength, so we can write it as wavelength is 2L, so f1 can be written as v by 2L. This f1 here is called as the fundamental frequency. So the term fundamental frequency basically states that this is the minimum frequency, that is the first starting frequency for any of these vibrations. Now there are multiple sets or the harmonic series that can form. So we already discussed this, that when you start with one vibration, you have one cycle that can end up forming two separate standing cycles to 3, 4 and so on, and therefore the amplitude from 2L it becomes L, 2 by 3L and half L. So the fundamental frequency is generally called as the first harmonics. It's still F1, which is V by 2L. So when you have F2, it becomes 2F1, so it becomes V by L. When it becomes 3V by 2L, and you get 2V by L. So this way you start going through the harmonic series, so which goes in the series of 1, 2F1, 3F1, 4F1. So in the range of natural numbers. Now each harmonic is an integral multiple of the fundamental frequency. So the harmonic series is a series of frequencies that includes the fundamental frequency and the integral multiple of the fundamental frequency. So for example, if you want to find Fn, the nth frequency, so it becomes n times V by 2L, so where n can be 1, 2, 3 and so on. So frequency here represents the harmonic number, which is n, which is the type of number of frequency that you want, over times the speed of waves on the string time over 2 times the length of the vibrating string. So next let's talk about standing waves in the air column. In an air column, so if both ends of the pipe are open, so there is an antinode at each end. So in this case all harmonics are generally present, and the earlier equation for the harmonic series of vibrating string can be used the same way. So we can use the same frequency for a pipe that is open on both ends. Now what if you have one end of the pipe closed? So when one end of the pipe is closed, there is node at the end, the open end, and so there is node at the closed end and antinode at the open end. Always remember, nodes form on the closed ends and antinode forms on the open ends. So only odd harmonics are present when you have a case where you have one side of the pipe to be closed. There the fundamental frequency, the formula for a harmonic series will be n times V by 4L, where n can be the series of odd numbers. Remember this, that this formula only applies to when a pipe is closed at one end. So this is the harmonic series. Let's try a simple problem. So they have given us what are the first three harmonics in a 2.45 meter long pipe that is open at both ends. What are the first three harmonics when one end of the pipe is closed? Assume that the speed of the sound in the air is 3.45 meter per second. So they have given us the velocity, so which is 345 meter per second. And they have also given us the length, which is 2.45 meters. Now let's start with, you have open ends. So open ends, the fundamental frequency F1 becomes V by 2L. So V by 2L is 345 by 2 times 2.45. So let's use a calculator and calculate the value. So you have 345 divided by 2 times 2.45. So that value becomes 70.4. So remember the unit for frequency is hertz. So F2 becomes, remember that it's open end, so it becomes 2 times F1. So it becomes 2 times 70.4. So that becomes 140.8 hertz. In the same way, EF3 becomes 3F1. So it becomes 3 times 70.4. So that becomes to 11.2 hertz. So this way we have the first three frequencies. Now they've asked us when one end of the pipe is closed, what would be the first three harmonics. So now let's try and write down the formula for F1. So F1 becomes V by 4L. So it becomes 345 divided by 4 times 2.45. So that gives you a value of 35.2 hertz. So now F3 will be the third frequency, so which gives you the value 3V by 4L or 3F1. So 3 times 35.2. So that gives you a value of 105.6 hertz. And the third frequency will be, the next one will be F5, which is 5F1. So it becomes 5 times 35.2. So that value becomes 176 hertz. So these are the frequencies when one end is closed, and these are the frequencies when it is open ends on both sides. So this is the way we can solve the problem. So next let's talk about timbre. So timbre basically refers to the quality of a tone that results when you have a combination of harmonics present at different intensities. For example, when you say have a clarinet sound different from a viola because of the differences in timbre, even when both instruments are sounding the same note at the same volume. So the rich harmonics of most musical instruments provide a much fuller sound than that of a tuning fork. For example, a tuning fork only produces one single harmonic, so one single harmonic frequency, which is the fundamental frequency, while you take a violin that can produce about 7 or 8 different harmonics at the same time. So this is the term timbre basically refers to. When you have a viola that can give you multiple harmonics, which results in a resultant waveform that's much more mixed in terms of all the wavelengths, which gives its distinct tone. Next, let's talk about beats. So whenever you have two waves that with slightly different frequencies interfere, so the interference pattern varies in such a way that a listener hears an alternation between the loudness and softness. So the variation from soft to loud and back to soft is called as a beat. In other words, a beat is basically a periodic variation in the amplitude of a wave that basically is the superposition of two waves with slightly different frequencies. So let's say, for example, we have two waves with slightly different frequencies. The waves undergo, at one point they'll undergo a constructive interference, and at 2 points they can undergo a destructive interference. The point at which it undergoes a constructive interference here is the point where we say a beat has occurred. So we can calculate the beat frequency. So the beat frequency is the difference between the first frequency and the second wave's frequency. So whichever is the greatest. Remember that the beat frequency has to be always be positive. So it can be F1 minus F2, or it can also be F2 minus F1. So it can be F1 minus F2, or it can also be F2 minus F1. Remember that the beat frequency has always to be greater than 0. So for this to be positive, so you have to put the larger value in the front. That's why we use the term F1 difference F2. So this refers to the value that it can be either F1 minus F2 or F2 minus F1, whichever gives you a positive answer. So this, with that topic, we end the topic on sum. I will see you again in the next lecture.